In section 14.3, I introduced the idea of derivative. Remember, we had a function of two variables here. We have some input x0, y0. We would be given some sort of unit vector, u equals ab. We would move a distance of h units to this new input, xy. We even found out how to parameterize that new input, xy. And we said that the way we're going to define the derivative is we're going to look at this change in z as x0, y0 goes from here to here. The functional value goes from this height to this height. So this is my change in my functional value. And as h goes to 0, so as this point moves closer, we'd be looking at what this height does. We want to know how z changes with respect to h. So we didn't call it, this is what we called it back then. But also we could have said this is dz dh. That's what we want. Okay, so we talked about what it meant and how we could envision that on a graph and all of that, but we couldn't compute it at that point. But we can now because of the chain rule. So the chain rule, z is a function of two variables. Okay? So I can take the partial with respect to x and with respect to y. But x and y are each a function of one variable. Remember, x0, y0 would be a constant. AB would be that unit vector, which would be given. So the only one variable here is h. So remember how that works. Z is a function of those two variables, which in turn are a function of one variable only. So z is ultimately a function of one variable. So we can find dz dh, the straight derivative. That's what this is going to be as h goes to 0. And the way we compute it is we take the derivative of z. We want to differentiate with respect to h, but z is a function of x and y. So we can differentiate z with respect to x and y, but then we chain that to be with respect to h. So this is a straight derivative because remember x is a function of one variable only. And the derivative, if you're going to differentiate this with respect to h, what's the derivative here? I have a times h. The derivative with respect to h is just going to be a. And the derivative of y with respect to h, here's y. The derivative of y with respect to h is going to be b. And so we get this partial of z with respect to x. Let me just write that as f sub x. Plus partial of z with respect to y. Let me write that as f sub y. This is how we're going to compute the derivative. Now, sometimes you'll see this, usually you'll see this written this way. If I think of this as f sub x, f sub y, dotted with ab, right? Think backwards here. What would this dot product be? fxa plus fyb. It's often written this way, and the reason why is because remember, AB, I guess I could have said that more clearly up here. U equals AB is a unit vector. That's the direction of our derivative, so that would be given. And so since I know this is a vector, we'll often write it in vector form. Now, one other thing that we do, just to make this easier to write this formula, is we introduce this notation here. This we call the gradient of f. The gradient of f, it's an operator. And the gradient of f is defined to be a vector where we take the partial with respect to x and then the partial with respect to y. But that's exactly what this is, partial x, partial y. So another way we could write this derivative is the gradient of f at x and y dotted with u. That's my dzdh. That's one and the same. So that's how we're going to compute the derivative. So for instance, find the derivative. Sometimes you'll see it called directional derivative, just to emphasize that it's in a certain direction. Find the derivative of this function at this point in this direction. So first of all, we're going to need a gradient. The gradient of f equals the partial with respect to x of this. Partial with respect to x. So that's going to be y squared plus 1 over x. And then the second component is the partial with respect to y here. So that's 2xy. And the partial with respect to y here is 0. There's no y's there. We need the unit vector, u. Now be careful here. This is tricky, and this happens a lot. They didn't give us a unit vector here. It said go in the direction of 3, 4, but that's not a unit vector. So we're going to have to find a unit vector here. Unit vector, to turn a vector into a unit vector, you divide by its magnitude. The magnitude of 3, 4 is 5. So u is 3/5, 4/5. So the derivative, which we'll take as the gradient, dotted with u, dotting here, I get 3/5 times y squared plus 1 over x, plus multiplying these two second components together, I get 4/5 times 2, so 8/5 x, y. So that's the general derivative. That would give me the derivative at any point x, y. We specifically want it at the point 1, 2. So here I could put an xy here. But the derivative at the specific point 1, 2 is going to be putting in a 1 for x and a 2 for y. We get 3/5 times 2 squared plus 1, so 5, plus 8/5. I'm putting in a 1 for x, and a 2 for y. So I get 16/5. 8/5 times 2, so 15 over 5 plus 16 over 5. So 31 over 5. Let's think back about what this means. We took the derivative, we get a number. Not a vector, we get a number. What does this mean? It means if we're on this surface for the input 1, 2, and we move in the direction of the vector 3, 4, this is the instantaneous rate of change of the function. That means the function, this is positive, so the function is increasing. And this number is a little bit bigger than 6, so if you thought about a slope, that's pretty steep. So this would be a good time for you to kind of take a look at GeoGebra and help you visualize what's going on here. This blue graph is this function graphed for us. The point 1, 2, x equals 1, y equals 2, this would be in the xy plane. We would actually be up here on the surface. We're going in the direction of 3, 4, our direction vector. I covered it up, but it was 3, 4. Whoops. Which means from this direction here, think of going 3 in the x direction, 4 in the y direction. So we'd be heading out in this direction. And that's what I've drawn here with this purplish plane, is where we would be on the surface heading out in that direction. So what we'd actually be doing, we'd be up here on the function. And as I head in this direction, so I'm coming out of the page a little bit, but I'm remaining on that surface, I would be going up some sort of cross section like this. And the steepness here, the rise over the run, I'm staying on the blue surface, is 31/5. So that seems reasonable. So you might want to go back to when I introduced derivatives in 14.3 and we talked about their meaning. We've already discussed all that. Now we can compute them. Going back to here, though, I want to look again at the definition as a dot product. If we look at this in terms of the way dot products are defined, we can get an idea of why this name gradient. So for us so far, the gradient was just a notation that told us what to do, but the word gradient sounds like it ought to have something to do with the steepness. This definition right here, this way of computing, is going to give us some idea about the meaning of the gradient, because remember, when you have a dot product, when you have A dot B, here's the other way of defining that. Magnitude, magnitude, cosine of the angle in between. So if we look at this version of the dot product, it's going to tell us something about that gradient.